In 1961, a meteorologist named Edward Lorenz was running a weather simulation on his computer. He wanted to rerun a particular calculation, so he typed in the starting values manually, but he rounded one number slightly. Instead of 0.506127, he entered 0.506, a difference of less than 1 part in 1,000. He expected the simulation to produce nearly identical results. What he got instead was a completely different weather pattern. The tiny rounding error had grown. Over time it had cascaded, amplified, and eventually produced a forecast that bore no resemblance to the original. That discovery became the foundation of chaos theory. Here's what chaos theory actually says, and it's important to get this right because it's often misunderstood. Chaos does not mean random. A chaotic system is fully deterministic. Every event follows directly from the one before it. There's no randomness involved. If you knew the starting conditions with perfect precision, you could predict the outcome exactly. The problem is perfect precision. In practice, you can never measure a starting condition with infinite accuracy. There's always some tiny uncertainty. And in a chaotic system, that uncertainty doesn't stay small. It grows exponentially. Two starting states that are almost identical diverge rapidly, and within a short time, they lead to completely different outcomes. This is what's known as sensitive dependence on initial conditions. Lorenz described it with a question. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The butterfly effect has become a cultural shorthand for a precise mathematical idea that small causes can have enormous, unpredictable consequences. The Lorenz attractor captures this visually. When Lorenz plotted his weather equations in 3 dimensions, the resulting shape looked like 2 loops of a butterfly's wings, the path swirling endlessly around 2 centers without ever repeating exactly. The system stays within a bounded shape, but it never traces the same path twice. Predictable in structure, unpredictable in detail. This turned out to describe a huge range of real systems. Weather is the most famous example. Meteorologists can give you a reasonably accurate forecast for the next 3 days. 5 days is possible with effort. 10 days is where real accuracy ends. Not because the computers aren't powerful enough, not because we don't understand the physics, but because the atmosphere is a chaotic system, and tiny measurement errors grow fast enough to swamp any forecast beyond a certain horizon. That horizon exists no matter how good the technology gets. It's a fundamental limit, not a technical one. The same structure appears in population dynamics. A simple equation describing how a population grows, crashes when resources run out, and recovers can produce behavior that looks completely random. Stable equilibria, then oscillating cycles, then sudden chaos, all from the same equation with different starting numbers. Ecologists found chaos in measurable animal populations in the wild. It shows up in the heart. The healthy human heartbeat is not perfectly regular. It's slightly chaotic in a specific way. A heartbeat that is too perfectly regular is actually a warning sign. Certain kinds of cardiac arrhythmia result from the heart falling into a different chaotic pattern, one that doesn't sustain effective pumping. Chaos in the right form turns out to be healthy. It appears in fluid dynamics, in the motion of planets over very long timescales, in electrical circuits, in dripping faucets. The dripping faucet, studied in detail in the 1970s, was found to exhibit chaotic behavior at certain flow rates, dripping in patterns that seemed random but were governed entirely by deterministic equations. What chaos theory showed is that the barrier to long-term prediction isn't always ignorance. Sometimes the universe simply amplifies uncertainty faster than we can reduce it. You could double the precision of every measurement ever taken, and a chaotic system would still become unpredictable just as quickly. A little later, but just as certainly. There's a philosophical consequence to this. For centuries, scientists assumed that better measurements would eventually give us better predictions, indefinitely. Laplace, a French mathematician in the early 1800s, imagined a demon that knew the exact position and velocity of every particle in the universe. For that demon, the entire future would be calculable. Nothing would be uncertain. Chaos theory doesn't exactly disprove that picture. Laplace's demon would still, in principle, be right, but it shows that any imperfection in knowledge, any limit on precision, even a tiny one, leads to predictions that fail. And since perfect precision is physically impossible, the future is fundamentally beyond our reach. Not because it's random, because it's too sensitive to what we can know.